In this assignment, we're going to start talking about exponents and logarithms. Now, if you remember from the beginning of this course, I told you there are only two operations in algebra, addition and multiplication. So a likely question would be then, what is an exponent? Is it another operation? No, it's part of multiplication. It's repeated multiplication. So let's talk about that before we look at some of the problems. If I were going to multiply 5 times 5, I can do this. And of course I get 25. But if I were going to multiply 5 times 5 times 5 times 5 times 5 times 5 7 or 8 times, that's going to get a little awkward. I would have to sit here and multiply or write out, and then I'd have to count 1, 2, 3, 4, 5, 6, 7. That's 7 5s. Well, that could get pretty bad if I wanted to do 125 of them. So what we've come up with is a shorthand. We call this 5 multiplied times itself 7 times, and we use the little exponent 7 to show how many 5s there are in that chain of multiplication. So that's all an exponent is. Well, let's look at some of the properties of exponents because of what they are. If I look at 5 to the second power times 5 to the third power, what does that really mean? That really means 5 times 5, that's the second power, times 5 times 5 times 5, that's 5 to the third power, and that's 5 to the fifth power. Oh. Well, what we do then is we just add how many times we're multiplying 5 together. We multiply it together 2 plus 3 times, which is 5 times. So when you are multiplying the same number with two different exponents, you add the exponents because that's how many times you're multiplying something by itself. So if I were to ask you what is x squared times x to the 7th, you'd say, oh, well, that's x to the 9th. 2 plus 7. Well, it becomes a little less obvious to us, but it is if you remember what these are. If I look at something like x to the 7th divided by x to the 5th, what is that? Well, let's write it out in multiplication. That's x times x times x times x times x times x times x. There's 7 x's divided by x times x times x times x times x. There's 5 x's. So on the top, the 1, 2, 3, 4, 5, 6, 7. On the bottom, there's 1, 2, 3, 4, 5. But we know that anything over itself is 1. And when you multiply what's left by 1, it doesn't change. 1 is the identity for multiplication. So I can say these two 1's here, or these two x's form a 1, these two x's form a 1, these two form a 1, these form a 1, and these form a 1. So what are we left with? X squared. X squared. That doesn't look too good. So, can we make up a rule about that? Remember over here, we added our exponents. Maybe we should subtract because 5 of those subtracted out. So, x to the 7th over x to the 5th, 7 minus 5 is 2. Well, that brings us up to the last thing we need to look at here. What if instead of x to the 7th over x to the 5th, I actually had x to the 5th over x to the 7th. Now we would have five x's on the top and seven on the bottom. And these still form ones. So we could say that this is 1 over x squared. But as I look at it and I apply what I applied up there, I took the 7 and I subtracted 5. Down here, if I take 5 and subtract 7, well, 5 minus 7 is minus 2. So 1 over x squared is the same as x to the minus 2 power. So now we've introduced a new concept, a negative exponent. A negative exponent just means 1 over. 1 over x squared. And it comes from the logic of saying that I take the number on the top and subtract the number on the bottom, and I get the exponent that results. Okay? So I wanted to show you those things first so you get a kind of a feeling of what are these exponents and what are they doing. So now let's take a look at some of the problems that are in our assignment. Well, what about 3 raised to the 2.4 power? Well, here we have something that's less than a whole number power, so I can't just say it's 3 times itself 2.4 times. And in fact, when you see something like that, what you need then is either a table or the calculator. So let me show you how to use the calculator to find the answer to that. We'll bring up our TI-84. Now first of all, we want to type in the base, so that's 3. And then we want to raise it to a power. Well, that's this little thing we call a hat. Raises it to a power. So for some of you, it'll just put the hat on the screen, and for some of you, depending on the how new your TI-84 is, it'll do like mine did and jump up into the exponent. But at any rate, at that point, you want to then type in 2.4 and then enter. So there's 3 to the 2.4 power. Now you could ask yourself, is that reasonable? Well, we know that 3 to the 2nd power, that's 3 times 3, is 9. And 3 to the 3rd power, that's 3 times 3 times 3, is 27. So 3 to the 2.4 must be somewhere between 9 and 27. And sure enough, it is. So there's a reasonable answer there. But that's how you do it. All right, let's go ahead and look at problem 2 here. Here we want to look at what it would be like to graph an exponential function. Well, some of you may have heard the expression that if something's growing very, very fast, we say it's growing exponentially. Well, growing exponentially means it's just taking off and growing rapidly. So that's what we should expect of this graph. So let's go ahead and graph some and figure some of these y values. If f of x equals 4 to the x, what is y going to be when x is minus 2? Well, what that means is 4 to the minus 2 power. But we learned just a minute ago that that means 1 over 4 squared. But 4 times 4 is 16. So that's 1/16. 1 to the, or x to the minus 1 power, or when x is minus 1, I'm sorry, it's 4 to the minus 1 power. That would be 1 over 4 to the first power, which is 1/4. Now what about to the 0 power? Well, the best way to illustrate that is go back to our fractions. What if I had x times x over x times x? Well, you would say anything over itself is 1, wouldn't you? X times x is x squared over x squared. Anything over itself is 1, so that should be 1. But let's use our rule that we determined in the last one. We said that this is really x squared over x squared. And when you have that, you subtract the exponents. Well, 2 minus 2 is 0. So x to the 0 power then is 1. And that's true for any number. Any number to the 0 power equals 1. So we'll put a 1 here. Now, 4 to the first power is 4. 4 to the second power is 16. So if we were to graph this, at minus 2, we said we had 1/16. Let's put 1, 2, 3, 4. So 1/16 would be way down here. 1/4 would be a little bit higher. When x is 0, y is 1. When x is 1, y is 4. And when x is 2, wow, it's way up there. So the graph is going to look something like this. And you can see now that as it goes out, it's growing very, very fast. That's why we say it's growing exponentially. So that's what the graph looks like. So what about this one? So they've given us a graph, and they've said, which one of these functions does that graph represent? Well, that looks just like the one we just did. What I notice is when x is 0, y is 1. So that looks pretty good. When x is 1, y is 3. That's a clue right there. When x is raised to the first power is 3. So that means the base must be 3. So this is just d here, 3 to the x. Now what would happen if we did some of the others? b, if I did 3 to the x minus 1. From translations that we've been doing with rational functions, most recently with quadratics, polynomials, we found out that when you subtract 1 from x, you move it to the right 1. So that would just move my whole graph there to the right 1. If I said 3 to the x minus 1, like f, notice the minus 1 is down on the regular line again, then that's going to take this graph and move it down 1. If I said minus 3 to the minus x, the minus in front of the 3 is going to flip it over the x-axis. The minus x is going to flip it around the y-axis, and we're going to have something that instead of going up like that, goes down like this. It's going to be in this quadrant down here. I'm sorry, it's going to go down like that. Minus 3 to the x would just be that one upside down, and 3 to the minus x would be that one flipped over that way. So translations still hold true for exponentials. Now, sometimes we have a problem to solve, and the problem is all up in the exponents. The unknown, the x, is all up there in the exponents. And we don't have a lot of ways to deal with things when they're up there in the sky, as I call it. So we have a notation for exponents called logarithms. Logarithms are exponents. They're not kind of like exponents. They are exponents. So when you see logarithm, think you're looking at an exponent. In this case, we see the log base 5 of 625. But what is that? Remember, equals means is. So it is 4. Meaning that 4 is the exponent. because remember I said a logarithm is an exponent. So when you see the word log, think you're looking at an exponent. And when it says it's equal to something, then that thing it's equal to must be the exponent. So 4 is the exponent. Well, let's see. There's got to be something raised to that exponent. We call that the base. The base is always the small little number by the log. It's a subscript to the log. In this case, it's the 5. So this is saying 5 to the 4th power is 625. Well, they want us to write it in exponential form. So to write this in exponential form, we would say 5 to the 4th power equals 625. But let's verify that, because we know what that means. That means 5 times 5 times 5 times 5. Well, 5 times 5, that first two, that's 25. But we still have times 5 times 5. Well, 25 times 5, remember 4 of them make 100, and one more would make 125. So 5 times 25 is 125 times 5. Now multiply that times 5, and you get 625. So 5 to the 4th power is 625. So what if we wrote this in logarithmic form? Well, remember I said that the logarithm is an exponent, and the exponent up there I see is 3. So I know that's the thing that's going to equal the log, because the log is the exponent. So right away I get rid of one of those things and put 3 over here, and now this is going to be the log. Now what's the base? Well, the base is the thing that's being risen to an exponent. So that must be the 8. And all that's left is the resulting number, 512. So there you see an exponential rewritten as a log. Let's take a look at this one, right in logarithmic form. Well, again, what is the exponent up there? What I see is an exponent of -2. So I know that that is what belongs on the other side of the equal sign. What's being raised to the -2 power? 4 is being raised to the -2 power, and the resulting number or value is 116. And sure enough, that's about right, because 4 to the -2 means 1 over 4 squared, which is 116. Now, how about this one, writing this one in logarithmic form? Well, first of all, I must introduce a new idea. This says the cube root of 27 equals 3. How do we express a cube root as an exponent? We express them as fractional exponents. The cube root, well, let's start with the square root. The square root of x is x to the 1/2 power. Cube root of x is x to the 1/3 power, and so forth. So the little number in the crook of the root is always the base, or the denominator of the fraction. Okay? So let's first of all write this in exponential form. So this says 27 to the 1/3 power equals 3. Now let's put it into logarithmic form. Well, the exponent is 1/3, so we know that's what equals the log. The thing being raised to the 1/3 power is 27, so that's the base. And the resulting number is 3. All right, so let's look at this one. Evaluate the following expression without using a calculator. Well, they gave us a log base 81 of 9. First of all, what are we looking for? We're looking for an exponent, because a log is an exponent. Our base is 81. So 81 to what power equals 9? Well, we can rewrite this as 81 to the x power equals 9. And that's what we call an exponential equation. And there's a way we can solve exponential equations. If both of the numbers, the bases on either side, are powers of the same number, we'll rewrite them as powers of the same number. And you'll notice 9 is 3 squared, so that's a power of 3. It's less obvious, but 81 is really a power of 3 also. It's 3 to the 4th power. So let's write that in terms of base 3. And we'll have 3 to the 4th power raised to the x power equals 3 squared. So all I did was I took the 81 and wrote it as 3 to the 4th power, and the 9 as 3 to the 2nd power. Now what do you do when you have something to a power raised to a higher power? You multiply the powers. So this is going to be 3 to the 4 times x is 3 squared. Now, if those things are going to be equal, then the exponents must be the same exponent. You can't raise a number to 2 different powers and have them stay equal. So if those are equal, and there are 3 is the base on both sides, then those exponents must be the same exponent. So 4x and 2 must be equal. So to do that, to solve for x now, I want to move the 4, so I'm going to divide by 4. So x equals 2 fourths. But simplifying that, that's 1/2. Oh, 1/2, that means square root, doesn't it? Well, let's ask ourselves, is the square root of 81 9? Sure is. 9 squared is 81. So x is 1/2. Okay. Let's go out a little ways here. Look at number 14. It says, use properties of logarithms to expand the logarithmic expression as much as possible. Where possible, evaluate the logarithmic expressions without using a calculator. Well, what we have here, remember that logs are exponents. We're looking for the exponent you put on 3 to get 9 times x. Now, what do you do with exponents when you're multiplying numbers? We said you add the exponents. So this is the same as saying then that we have the log, the exponent you put on 3 to get 9, plus the exponent you put on 3 to get x. Because we were multiplying the 9 times the x, we can add the exponents you put on 3 to get those. Well, let's see. Log base 3 of 9. What's the exponent you put on 3 to get 9? Isn't 9 3 times 3? It's 3 squared. So this is just the exponent of 2. Now, since we don't know what x is, we can't simplify any further or expand any further. The log base 3 of x has to stay the log base 3 of x. So this becomes 2 plus the log base 3 of x. And that's the answer they're looking for here. Well, let's see if we can do one that has a little more complication to it. Can we expand this one? Well, as I look at the expression in parentheses, what I chiefly see is a fraction or a division going on. That's 8 divided by the square root of x plus 2. When you see a division, if you remember back from what I was doing a little while ago, you subtract the exponents. Logarithms are exponents. So this becomes then the log base 2 of 8 minus the log base 2 of the square root of x plus 2. Oh, let's see. Log base 2 of 8. Is 8 an even power of 2? I believe that 8 is 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So that's really 2 to the third power. So we can say log base 2 of 8, the exponent is 3. Now the square root, we learned that we don't really want to use radical signs anymore. We want to deal with it as an exponent, and the square root is a 1/2. The exponent is 1/2. So this would be 3 minus the log base 2 of x plus 2 to the 1/2 power. But I can do something, one more thing. I have an exponent of something raised to an exponent. And when you have that situation, you can multiply the exponents. Remember, the log is an exponent. So this becomes 3 minus 1/2 times the log base 2 of x plus 2. But I can't go any further. I cannot take and separate a log of a sum because logs only deal with multiplication. So can't go any further than that. That is expanded as far as it can go. Now what if we were going to go the other way and condense? Meaning put it together, shrink it. Well, we have the log of 50 plus the log of 20. There's no little number down by the g. When you do not see a little number down by the g, you can assume, correctly assume, that it is base 10. So this is the exponent you put on 10 to get 50. Well, there is no exponent that we know of to put on 10 to get 50 because 50 is not a power of 10. Be careful. It's 5 times 10. That's multiplication. But you can't do 10 times 10 times 10 times 10 any number of times to get 50. So therefore, we don't know what it is, but there is one, log of 50, and then we want to do plus the log of 20. But we're adding 2 exponents. What are you doing to numbers when you add their exponents? Well, going back to the beginning of this lesson, we learned that you add exponents when you're multiplying numbers. So that means that this is really the same as the log of 50 times 20. I'll put that in parentheses, which is the log of 1,000. Oh, wait a minute. 1,000. Maybe that's a power of 10. Let's see. 10 times 10 is 100, and 100 times 10 is 1,000. That's 10 cubed. So what's the log of 1,000? Base 10? 3. So your final answer is just 3. Who would have thought that all of that up there, log 50 plus log 20, would be just 3? But it is. Okay, so that's 16.